Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. Just wanted to post another problem solution today and kind of discuss some of the properties about airflow in pipes, gas flow in pipes. Also wanted to point out that if you have any specific engineering problems you'd like me to cover in addition to the ones that are in this book, just let me know and I can take a look at it. It doesn't have to be from a book. It doesn't have to be from this textbook, but you could also give me suggestions from another textbook that you have, or any other engineering centered textbook. I have experience in a lot of different fields. I am a chemical engineer by trade, but I enjoy doing problems from lots of different fields. And I have experience in a lot of different fields. So just let me know and put something in the comments or send me an email, and I'll be able to help you out with that. Anyway, we are doing a problem from Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 5.10. A stream of air enters a 7.5 centimeter inner diameter pipe at a velocity of 60 meters per second at 27 degrees Celsius and 1.80 bar gauge. At a point downstream, the air flows through a 5 centimeter pipe at 60 degrees Celsius and 1.53 bar gauge. What is the velocity of the gas at this point? Well, if you're constricting the flow, it's going to be constricting the pipe, the inner diameter. The amount of mass, if you're going to have the same amount of mass flowing in one end of the pipe out the other end of the pipe, there's no accumulation inside of the pipe, then the mass is going to, the velocity of the fluid is going to have to increase when you shrink the pipe down. It's like putting your thumb over the hose at the end of the hose. The water is moving through the hose, you put your thumb over the end, the same amount of mass has to go through the hose. The amount of mass in the hose isn't going to build up, right? So what has to happen is it shoots out the end that you've constricted. So instead of having like a slow laminar flow through the hose, it kind of sprays out really quickly. That's kind of what's happening inside of this pipe, if you can get a good picture of that in your head. I did have to make some corrections to this problem after I'd already recorded the video. That's why you see these weird highlights here that are in black. Those are the old highlights that I did, and then after I started working on it, I was like, hold on a second, I made an error. So I just went through. It's a short video, so I'm just going to redo the video here so that you guys can see how to do the actual solution here. Okay, so this is the information they gave to us in the problem statement. The important concept here is that mass is conserved, okay? Like I was saying, the certain amount of mass going in the pipe has to come out the pipe at the other end, right? Okay, mass is conserved. Well, there's no chemical reaction going on, so in fact, there's no, the amount of moles is also conserved, okay? So let's take all this information that we got up here and turn it into more usable information so that we can use our ideal gas law, okay? Pipe 1, we have our pressure here, and you have to use the absolute pressure, not the gauge pressure. So this is the gauge pressure plus the absolute pressure, and gives us this in pascals. Have to use absolute temperature, so we convert this into absolute temperature. Got our inner diameter of the pipe, going to convert that into meters, so it's in SI units. Here's an important characteristic here. We've got a pipe, and then we have stuff flowing through the pipe, right? If this is the cross-sectional area of the pipe, right? You have stuff moving through the pipe. Well, if you wanted to know a volumetric flow rate, you would kind of take that cross-section and you would say what's the velocity moving through that cross-section. And if you assume that you've got the same velocity moving through the pipe, like this is an average velocity that they gave to us, then you can just multiply it by that cross-section that it's flowing through, and that'll give you the volumetric flow rate, okay? So this is the cross-sectional area. This is a circular pipe. A pipe is circle, so you just multiply it by pi r squared, right? Okay, because that's the cross-sectional area of the pipe. So in order to get the volumetric flow rate, cross-sectional area times the flow rate, and you get that, okay? And then we do the same thing over here with pipe 2. Temperature, change that into Kelvin. Pressure, change that into pascals. And our inner diameter, okay? Then we've got our cross-sectional area over here, but we don't know what the velocity of the fluid is. But in order to calculate that, we'll need to find out what the volumetric flow rate is, and we already know what the cross-sectional area is, but we'll divide by the cross-sectional area. We've got our moles conserved. That means that this statement is true, okay? The R cancels out because they're the same constant, okay? And we solve for V2. Solve for V2. Okay, so this is rearranged here, and we already know what all these are. I just showed what those are, and it calculates out to this, and then we divide. We just use this equation right here, and we divide that by the cross-sectional area that we got before, and we get that our velocity in the pipe, when you constrict it down, is 166 meters per second. Okay. Thank you for watching. I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problem you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.